So we finished talking about the solar system last time, and now we're going to talk about planets outside of our solar system before we move on to talking about life in the universe and then stars and galaxies. So today we're going to be talking about exoplanets, which are planets that orbit stars other than our sun, and we'll learn how we can detect them and what we've learned by studying these exoplanets. So if we remember back to learning about Uranus's moons, there were different names for the moons like Puck and Matilda. So you don't necessarily need to know this, but I think it's a fun bit of trivia as to where those names come from. Yeah, so they are from both Shakespeare and Alexander Pope. So they're from English poets. So a lot of solar system stuff is named after Greek or Roman mythology, but Uranus and its moons were discovered later, and so they're named after English poetic characters. So we'll start by talking about how we detect planets around other stars. But this is a very difficult thing to do. So stars are the things that are going to be emitting the most light. So planets are not really going to emit a lot of their own light. And so you have a very bright object next to something that's very faint, and the sizes and distances to these things are pretty extreme. So the analogy is trying to detect a planet around a distant star is like trying to see a pinhead 15 meters away from a grapefruit in Washington, D.C. if you're observing it from San Francisco. So very hard to do. But we have developed several techniques that we can use to detect exoplanets. So these are the most common techniques: radial velocity method, transits, astrometry, pulsar timing, direct imaging, and microlensing. So we'll talk about each of these different techniques. So this is a graph of the number of exoplanets detected and by which method they were detected. For a while, the most common was the radial velocity method, but recently there have been a couple of space telescopes that have been launched that are very good at detecting exoplanet transits. So you can see after those satellites launched, the green bars, which are the transit method, really exploded. And on the y-axis, you can see we've now detected thousands of different exoplanets. So the transit method basically looks like this GIF. So if you understood the geometry of an eclipse on the Earth, this is basically the same thing. Except now instead of the moon and our own sun, it's a planet and the star that planet is orbiting. So when the planet goes in front of the star, it will block some of the starlight, and so there will be a little bit of a dip in the brightness of the star. When the planet goes behind the star, it won't be reflecting any of the starlight towards the Earth, and so there will be another little dip called the secondary transit. So here's that kind of geometry in a still image. So in positions 1 and 2, the planet is not really blocking any of the starlight. Then in position 3, it's blocking the maximum amount of starlight. Then it goes back to not being in front of the star, But for example, position 4, some of the starlight that would be going back behind the star and out into space that way is actually being reflected off of the planet and towards the Earth. So there's a little tiny bit of rebrightening right before the planet goes back behind the star, and you get the secondary dip. And so the transit is when the planet goes in front of the star, and then when it goes behind the star, it's an eclipse. And so the technique that we use to find this pattern is you just point your telescope at a star and you take a bunch of data, and over the course of, say, weeks or a year, if you take a data point every day, then there might be some days where there's a lot less light, or not a lot less, but a few % less light coming from the star. And if you observe that happening at a regular period, then that's evidence for this planet orbiting the star. And the size of the dip is going to tell you the relative size of the planet with respect to the star. So a bigger planet will produce a bigger dip, and a smaller planet will produce a smaller dip. Sometimes the geometry of the system is not set up in such a way that the planet is going to pass in front of the star, so it will never block any of the star's light. However, because the planet can reflect some of the starlight towards the Earth, there is a technique that you can use called orbital brightness modulation, where over the course of this planet's orbit, it will be reflecting different percentages of light back towards the Earth. And so it will appear that the star is at times getting brighter and then getting fainter again. And this is only going to be fractions of a percentage, but we have very good telescopes that can detect that small variation in the brightness of a star. And kind of the crux of all of these techniques are that, for the most part, in their lifetime, stars' light output is very constant. So we'll learn about that in a couple weeks when we talk about stars. But for the most part, the light output from a star would just be a flat line. And so any deviation from that flat line is evidence for, say, an exoplanet. When I've talked about, for example, things in the solar system, I've said that they're orbiting the sun. And that's mostly right, but the more accurate thing to say is that everything in the solar system, including the sun, is orbiting the center of mass of the solar system. So obviously, planets are very far away from this center of mass, and it just looks like they're orbiting the sun. But if you look at the sun's motion, the sun itself is actually moving. And so it's orbiting about the point that is the center of mass of everything in the solar system. And so this period of the sun's motion about the center of mass of the solar system is about a 12-year period. And so if you were to be in some other solar system looking at the sun, then you would see it moving, and that's evidence that there's other masses in the solar system that are causing it to orbit this center of mass. And so we can use that technique to detect exoplanets around other stars. One of the ways that we can do that is with the Doppler technique. So let's say we are observing a star, and at sometimes we see the star's light being blue shifted, and then at other times we see that star's light being red shifted. That's evidence that this star is orbiting the center of mass of its solar system, and that's evidence that there has to be other mass other than the star's mass in that solar system. So we can measure these Doppler shifts for motions that are as small as 1 meter per second. So that's like walking speed for a human. So we have very sensitive instruments that can detect these kinds of motion. And so as an example, you might have the middle spectra where these lines match up very nicely with, let's say, hydrogen absorption features in the star's atmosphere. But then sometimes those lines will be red-shifted, so they'll have less energy. And then at other times, those lines will be blue-shifted, meaning they have more energy. And so using the spectra of a star that you take, say, every day over the course of several weeks or months, you can detect any motion that that star is doing. So now that you've collected all of that velocity data this is over the course of a week for the star, if you plot the velocity of the star over time, you might get a graph that looks like this. So what's happening is, as the star is orbiting around the center of mass of the system, sometimes it has no Doppler shift, sometimes it has a maximum Doppler shift of -50 or +50. And this looks like a sinusoid or a cosine graph, and we can use the time from the peak to peak or the trough to trough to calculate the period of this star's orbit. So once you have the period of something's orbit, you can use Kepler's laws to figure out what mass must be causing this orbit. And so using this technique, we can actually figure out the mass of the exoplanet that's causing the star's motion. And the first exoplanet that we found using the radial velocity method was back in 1995. Not everything is oriented in such a way that the star is moving towards you or away from you, but you can still use the motion of the star orbiting around the center of mass to try to detect the presence of an exoplanet. So this is the astrometric technique, and this is basically tracking the position of a star over the course of, in this case, 30 or 50 years, 60 years, to see if it's moving at all. So this is a model of what the position of the sun would look like over the course of time if you were observing it from 30 light years away. And so, of course, our solar system has a lot of different masses, and so the position of the center of mass is going to change depending on how the planets are distributed around the sun. So that's why we don't get a nice consistent circle. We get this kind of weird loopy circles where it doesn't always return to the same place. This is very hard to do. So you can see you have to get to 1,000th of an arc second, and an arc second is already 1/3600th of a degree. So these are very small changes in the position of a star on the sky. But again, we have very sensitive telescopes, and we are able to detect some of these motions caused by orbiting planets. And I said it's very hard to directly take a picture of a planet, it's like taking the picture of a pinhead orbiting a grapefruit in Washington, D.C. if you're in San Francisco, but we've actually managed to do that. So these are images from the Large Binocular Telescope and the Keck Telescope. So these are in infrared, and so the planets have the right temperature to actually emit light in the infrared. And they've just taken something to put in front of their telescope to block the light from the star, and that allows you to directly image the planets that are orbiting the star. And then you can put those pictures together over the course of several years to get a little movie of how those planets are orbiting around their host star. So this technique, gravitational microlensing, is pretty interesting. It comes back to general relativity. So in space, you can have something like a star that's emitting light, and if there was nothing in between us as the observer and that source star, then the light should just travel in a straight line and make it to our telescope. However, the presence of mass in between the source star and the observer will distort the space-time in between us and cause the light to no longer travel just in a straight line, but to be bent around that curvature of space-time. Obviously, stars are much more massive than planets, so they will distort the space-time the most, but planets also have masses, and so that little distortion in space-time by the planet is something that we can detect. So these microlensing events can manifest in a couple of different ways. One way is that this singular source can get split into what appears to be 3 different images on the sky. So we use a technique called ray tracing, and so if this planetary system wasn't in between us and the source star, we would just get a photon straight from the star to our telescope, and we would see that as one object. But because this light is getting bent around the system, we might see, for example, 3 different images. So this light ray should be coming down here and completely miss the Earth, but because of the mass of the system, it actually gets bent back towards us as the observers. So when we look through our telescope, we trace this line back to where it should be in space if it just came to us in a straight line. So we would actually see an image of this source star down here. And then we do the same thing for these other 2 lines. This line gets bent, it hits our telescope, we trace it backwards, and we would get us 2 sources up above where the star actually is. So the microlensing can produce multiple images of the same star, or it can also magnify any background images. So there's a couple different results of this microlensing that, if we detect it, we can use it to infer if there is a planet and what mass that planet has, because the amount of distortion of space-time is just dependent on the mass of the object. Another technique, and this was the first technique that was used to find an exoplanet, is pulsar timing. So pulsars are rapidly spinning neutron stars. We'll talk about neutron stars a bit later in the semester, but they emit light in a very narrow beam, and they're rotating very quickly. So when this beam is directed towards the Earth, we see it as a very bright flash of light, and that flash of light happens at a very consistent period. So if we detect one of these pulsars and its period seems to change at a regular rate, we can infer that there must be an exoplanet orbiting this pulsar that's causing its the period of its spin to change slightly. And so this is kind of the movie of what the pulsar might look like. Depending on the orientation of the beam, you might get both flashes that you detect, or in this case, only one of the beams ever points directly at the Earth, so we only get one peak. And then this is what a pulsar might look like in the sky. So this is when it's really bright, that's when you're getting all of the beam, and then there's kind of a little secondary brightening where you're getting part of the opposite side of the beam pointed towards the Earth. So scientists are pretty smart, and we've come up with a lot of different ways to detect these exoplanets around other stars. It's hard to image them directly, so we use a lot of indirect techniques like the Doppler shift method or exoplanet transits. And a lot of the methods that we use most often require very specific geometries. For example, the Doppler shift and the exoplanet transit method really need you to be looking edge on at the other solar system. So now we're going to talk about using those methods, what things can we measure about these exoplanets. The most important thing that we could get from our measurements is the density of the planet. Because once we know the density of the planet, then we can decide, is it a gas planet, is it a terrestrial planet? And in order to get the density, we actually need both the Doppler shift method and the exoplanet transit method. And another thing that we're going to be able to measure, if conditions are right, are the atmospheres of these exoplanets. So with the Doppler shift method, we will never get an exact value of the mass, and that's because we don't know the exact orientation of the orbit. So if the orbit was exactly in line with our line of sight, then the mass we would be measuring would be the mass of the planet. But the plane of the orbit of the planet might be tilted from our line of sight, and so all we can really say is the lower limit of the mass of the planet. And if you are able to detect the exoplanet in several different ways, you can mitigate this kind of flaw in the Doppler shift method. So the top is the light curve. So when you take a series of images of an object in space and you plot its brightness over as a function of time, we call that a light curve. So this is the light curve for the TRAPPIST-1 system. And all of these dips in the light curve are actually exoplanet transits. So this particular system, we've detected 7 exoplanets in this one system. Using the transit method, we can calculate the radius of the exoplanet. And so for this system, all of the planets are pretty similar radius to the Earth. So Some of them are within 5% of the Earth, and the farthest away is not quite 30% away from the radius of the Earth. So how do we get the mass from the Doppler technique? So in lab, we saw how we could use the spectrum and how it shifted to measure a velocity of something's motion. And so you take the energy or wavelength or frequency of the light when the object is not being Doppler shifted, or when it's not being Doppler shifted on the bottom, when it is being Doppler shifted on the top, and using this equation you can calculate the velocity of the star. Then doing some combining some equations about orbital motion, using the velocity of the star, the period of its orbit, and some constants like pi and the gravitational constant, you can calculate what mass of exoplanet you needed to cause the motion of that star. And so using this equation, you can calculate the mass of the exoplanet. Then from the transit method, we're eventually going to get the radius of the planet. We'll start by getting its velocity from the period of the exoplanet's orbit and the radius of its orbit, so how far it is away from its host star. Then using the shape of the dip of the exoplanet, we can calculate the radius of the star, or as we'll talk about when we learn about stars, using the spectra of a star, you can classify its type and basically just assume the radius of the star given its spectral features. Then, but you can also do it just using the graph of the transit. So if you have the velocity of the planet and you measure the time of the dip, then you can calculate the radius of the star. So this is not too dissimilar from the technique that the ancient Greeks used to calculate the distance from the Earth to the Moon using the lunar eclipse. Once you know the radius of the star, you use the height of the dip, so the percentage of light that's being blocked, to calculate the radius of the planet. So the amount of light being blocked is a function of the area of the planet, so these should be radius squared. The important thing is the amount of light that's being blocked, that percentage is related to the radius of the planet. So now we have the radius of the planet from the transit method and the mass of the planet from the Doppler shift method. Using the radius, you can calculate the volume, and then dividing mass by volume, you can get the density of the exoplanet. And the density is very important because it tells us if it's a rocky planet, so maybe it could have life like we find on Earth, or it's a gas planet, and so it's probably not very conducive to life. The other interesting data that we can get from the transit method is information about the atmosphere of the exoplanet. So to do this, we need to take data from when the planet is not in front of the star, when it is in front of the star, and then when it's behind the star. So we need the transit and the eclipse. So the data that we get might look something like this. So when the planet is in front of the star, you're getting any emission features from the planet. You're getting the black body curve of the star. You're getting any absorption features of the planet's atmosphere absorbing some of the star's light, and then you're getting the black body curve of the planet itself. So during the transit, there's kind of too much going on. So you need other data points to basically subtract away what's going on. So when the planet is next to the star, so not in front or behind, now you're getting the black body emission from both objects, and you're getting the emission from that planet's atmosphere. And then when the planet goes behind the star, now you're only getting the black body curve from the star itself. So if all you care about is the atmosphere of the exoplanet, you want to subtract away the black body emission from the star. And so if you did that from this picture, you'd be left with the black body curve of the exoplanet and then the emission features of its atmosphere. Then, if you want the absorption features of the atmosphere, you would take the black body curves and subtract them away from this top image, and you'd be left with the absorption features of the atmosphere and then the emission features of the atmosphere. And so if you have all of this data and you're able to subtract away the parts you don't care about, like I just mentioned, then you can get data on what chemicals are inside of that atmosphere. So, for example, if you're looking for a place to send humans in the future, maybe you're looking for a lot of oxygen in the atmosphere so people can breathe without a spacesuit. So, very useful information that we can get using this technique. So that's the type of data that we can get from these exoplanets. So we've done these studies. Now let's compare what we see around other stars to the planets that we have in our own solar system. So Kepler and TESS are the two satellites that I mentioned that were launched to study the exoplanet transits, and they've measured between them thousands of exoplanets, and so we have a lot of data to play with. So I said we have very sensitive instruments, but the science that these instruments are doing is still very hard, and so there are some biases in the data that we've collected. So most of the planets that we have detected around other stars have orbits that are closer to their star than Jupiter's is to the sun. So it's harder to see planets that are farther away than that using the techniques that we use at the moment. And then something interesting that we've seen are that planets in these other solar systems have more eccentric orbits than the planets in our solar system. So all of the planets in our solar system have almost circular orbits, but that's not the case for the planets that we've observed in other solar systems. If you make a graph of the orbital period versus the radius of the planet for so some of the planets in our solar system and then the exoplanets, you get something that looks like this. So that's not to say that there aren't tons of planets that have longer orbital periods, it's just that it's very hard for us to detect those. So you can see there are some planets that are so close to their stars they have an orbital period of 1 day or less, and some of those planets are even bigger than Jupiter, for example. What we've seen from these two missions are that planets around other stars are very common, and just using statistics, there have to be more planets than stars in the Milky Way. So our solar system is not unique. Most stars have some kind of planetary systems around them. And smaller planets are going to greatly outnumber large planets. And again, that's something that basically in any field of study, this is going to be true, where smaller things outnumber the larger things. Another interesting graph we can make, so on the x-axis we have the mass, and on the y-axis we have the radius. These dotted lines are different densities. So the far right dotted line is the density of iron, then the center dotted line is the density of water, and then the far left dotted line is the density of styrofoam. So we can see where the different planets in our own solar system and where the different planets, exoplanets we've detected fall in these density lines. So for example, Venus and Earth are the two green dots at the bottom, with density somewhere between the density of water and the density of iron, which makes sense. We have an iron core, but then we have rocky material and water on the surface. Venus also has iron core and rocky material. Then the gas planets, some of them, like Saturn, are less dense than water. Some of them, like Jupiter, are more dense than water. But you have really weird planets like super-Earths. So these are planets that are terrestrial but have a larger radius than the Earth. And for example, this one has the same density as iron. So maybe that's just a solid ball of iron that's orbiting a star. And then you also have really weird planets. So this one has a larger radius than Jupiter, but it has a very low mass. So this one has the mass of styrofoam. So it must be made out of gases, but not dense gases at all. So a lot of interesting things that we can take away from this. Another category that we have are water worlds. So in our solar system, some of these are just gas planets that are kind of colder and farther out from their star, but maybe some of these are planets where there's just the entire surface is covered in a liquid ocean. And so again, when we're thinking about where we might find life out in the universe, a place like a water world could be a very interesting candidate. So some of the interesting things that we've seen, there's highly elliptical orbits for some of these exoplanets. There's a big range in sizes and densities. And there are a couple of classes of exoplanets that we don't have in our own solar system. So one of those are called hot Jupiters. And so those are gas giants that are orbiting their stars very closely. So in our solar system, we only have rocky planets orbiting close to the sun. So we've learned about the different things we can measure from exoplanets, and then putting those measurements into context with respect to comparing them to the planets in our solar system. So now let's revisit our theory of the solar system forming with this new data that we have. So before we were studying exoplanets, we only had one data point, which was our own solar system. But now we can study many other planetary systems, and so we can revisit our theory of the solar system forming. So to review, the nebular theory for solar system formation, we had a big cloud of gas that started to collapse, forming a disk. The center of the disk was the densest part and the hottest part. That's where your star is going to form. Then closest to the center is very hot, So you have the frost line where there's rocky material inside and icy material on the outside. Then you have the star forming in the center, planetesimals and planets forming outside of that. And then once the star turns on, doing nuclear fusion, it kind of blows out any remaining gas that's left over. So that was the theory we made when looking at our own solar system. But we have detected something that disagrees with that theory. So these hot Jupiters couldn't form in our model that we came up with. So there's no way to get a gas planet forming close to the star. The modification that we made to the nebular theory is this idea of planetary migration. So in essence, we think that these gas planets did form outside of the frost line of their stars, but some kind of gravitational interaction has caused them to move closer to their stars. So one of the ways that can happen, so if you have your protoplanet forming here, the mass of this planet can basically create a ring of material that won't be able to coalesce into a planet. So kind of like how the asteroid belt was never allowed to form a planet by Jupiter. Then all of this distributed mass will tug on this gas giant, causing it to start to orbit closer to the center of the solar system, so going closer towards the star. The other thing that could happen, what if you have two gas giants they get too close to each other, and instead of colliding with each other, one of them gets pushed closer towards the star, the other one could get ejected from the system or find itself on a highly elliptical orbit. And then we talked about how resonances they're responsible for the different gaps in the asteroid belt. Maybe different orbital resonances can disrupt some of the gas planets enough that one of them will start orbiting closer to their host star. So when we did that census of all of the planets that we've seen, we do see gas giants and terrestrial planets like we have in our solar system, but we've seen different classes of planets that we don't have. So, for example, hot Jupiters. We also found planets that were smaller, much smaller than Neptune, but that have densities that lead us to believe they still must be made out of gas. Then we saw water worlds. We found super Earths, so terrestrial planets that have much larger masses than the Earth. And then, of course, there are exoplanets orbiting binary stars. And again, we've only just scratched the surface on what type of exoplanets we can detect out in space. So there's many more exciting discoveries waiting to be made. So which of these is the most accurate way of describing how planetary migration might happen? So the gravity one is not right because it says the gravity causes you to push something, and gravity is a pulling force, not a pushing force. And then the mass is not going to make it orbit closer to the star, and we didn't talk about magnetic fields at all. So It just has to do with the energy being transferred and orbital or angular momentum being transferred when things interact in their orbits. So by looking at other planetary systems, we had to modify our nebular theory, and the modification that we made was that planetary migration can cause things like a large gas planet to start orbiting its star much closer than it could have originally formed. So we will keep our information about exoplanets in mind next time when we talk about our prospects for finding life elsewhere in the universe.